usual, this is a little 10-minute talk of what's up in the night sky in the next month. The picture is taken by Steve O'Meara, and I'm going to talk more about that in a moment. Normally, when I introduce these talks, I give as reference the Collins 2023 Guide to the Night Sky, which is very useful. It has 2 maps for every month, one facing north and one facing south. The other reference I give is Night Skies of Botswana by Stephen O'Meara. That has 4 maps for every month, one to the north, south, east, and west. And now, where I'm differing this month in my presentation, I'm going to say if you want to know what's up for next month, go and look at those 2 references. I'm going to make a little bit of a difference. I'm going to talk about the past, the future, and the future plus. So there you see, Geraldine and I spent a night at Magadi Pans with Deborah and Steve about 10 days ago, and it was a night to remember. It was pitch dark. It was the 17th of June. It was new moon, and the sky was too magnificent to behold. The sky and the stars, planets, galaxies. It was just incredible, and Steve brought it to life. That's a picture which he took, and you can see in the foreground are a couple of bedrooms. You can't see the walls because there aren't any, and this is there were 12 of us lying in our beds in bedrolls, looking up at the night sky during the night. This was a photograph that Steve took of the small Magellanic Cloud and the large Magellanic Cloud, which are the largest dwarf galaxies in the Milky Way's retinue. This was a picture of the Milky Way as seen on that night by Steve. How it went was that Deborah, his wife, did a yoga session in the afternoon. Then we had supper. Then Stephen spoke to us for about just over an hour. Then we went to bed, and he stayed up all night taking photographs. The man is incredible. He brought that, as I said, he brought this night sky to life. And I was just sorry that there weren't more people in Botswana who recognize this incredible heritage which we have, and that we're able to benefit from his stories. During the evening, we saw Venus shining brightly in the west with Mars and Regulus. At midnight, we spotted Saturn directly overhead. And in the pre-dawn, we saw Jupiter dominating the sky, and we were very lucky to see the International Space Station just float past Jupiter. That is a photograph of Andromeda taken by Steve during the night. I must be a negative. I don't know why it's so light colored, but he could probably explain later, make a contribution. Incidentally, the Milky Way will collide with Andromeda in 5 billion years, so brace yourselves. It's going to happen. If these guys predict it's going to happen, know that it's going to happen. That was a photograph of a cluster, an open cluster, the wild duck cluster. Unfortunately, I didn't see it. That was one of the photographs that Steve took in the middle of the night. It's very impressive, but you're supposed to be able to see wild ducks there. I can't, but maybe they're the small ones inside there. I don't know, but it was a very good photograph. Now, the big 5 of the African sky. Most tourists come to Botswana to see the big 5. They're elephants, lions, leopard, buffalo, and rhino. But there's also a big 5 of the African sky. Open star cluster, globular star cluster, bright nebula, dark nebula, and there are millions of galaxies, but the best one of all for us to see is the Milky Way galaxy. Steve pointed all of these out to us. And here's a photograph. Steve didn't take this, but I've got it, and we saw all of this as it was. The now up at the top, just off the screen, is Omega Centauri, which is the most magnificent globular cluster. Down here is Eta Carina, which is an open cluster, which is fantastic. No, that's not right. Southern Pleiades is over here, which is an open cluster. Eta Carina is a magnificent nebula. A dark nebula is given by this, which is the Coalsack. And of course, the most magnificent galaxy is the Milky Way. Now, as I mentioned, I was just sorry that we couldn't share this with anyone. We couldn't share all of this. And I feel frustrated that probably less than 1% of people know about the light sky, 1% of people in Botswana. I just feel we need to do something, and I'd like to make a recommendation. If you go to the States, in every state has a nickname. So in the top left, Montana, Blue Sky Country, New York, Empire State, Texas, Lone Star State, and all these little nicknames are on every license plate of every car. So within a minute of driving into Montana, you know that it's Blue Sky Country. Hawaii, Aloha State. Alaska, the last frontier. Now, I thought maybe we could speak to the authorities and maybe say Botswana, Milky Way country, or Land of the Stars, or Capricorn, and I can't see what I wrote there, Capricorn country. We should publicize this magnificent night sky which we have. 3 nights every month in winter, from June, July, August, September, you can almost guarantee that there have been, if you go out into the open, away from the cities, you'll have every month 3 nights of clear skies, no clouds. That's 12 days. These are 12 magnificent days. And I know there are many, many people in the Northern Hemisphere who would love to come and see what we've got to show. And yet we don't know it. We don't publicize it. It's unknown. It's such a waste of tourism opportunity going begging. So I'd like to suggest somehow or other we can advertise our night sky better. Another aspect is we have advertised very nicely. The museum has, where the Tropic of Capricorn crosses the road between Gaborone and Francistown, they've got a very nice little display. It's called the Tropic of Capricorn display. But it doesn't link to the constellation Capricorn, which I've drawn there. It doesn't say why it's called the Tropic of Capricorn, which is sad. And as I said, I don't think 1% of the people in Botswana could point out the constellation Capricorn. They don't know about it. And they don't know why it's called the Tropic of Capricorn, as they don't know why it's called the Tropic of Cancer. So I'd like to suggest that also we speak to the museum and say, congratulate them on what they've done. But they also put up a huge model made of metal of what the Tropic of Capricorn looks like. And they also put up a model in metal or steel of showing all the zodiacal constellations. People don't know them. They know astrology, but they don't know where those constellations are and what order they go and what it's about. We need to educate people, and it's a very simple education to do, so people will ask questions and then become interested. So I've had that little rant. Let me say that, let me talk about the future. And the most exciting event this month is on the 29th of July, when Venus, Mercury, Mars, and Regulus can be seen in a small group in the west at 5:45. You'll have to look sharply because 5:45 is when the sun is setting. So you'll see them faintly in the west, all of those 3 planets and Regulus. Regulus is in Leo. more exciting is new moon is on the 17th of July, which occurs on the President's Day long weekend. I can really recommend to as many people as possible to go out into the desert, into wherever they can, away from the cities and towns, and look up at the night sky that night. If you're not going to go to Makgadikgadi, you can go into the bush, go to Kutsi, go anywhere you like. You won't get as good a view because Makgadikgadi has got no trees, no hills, nothing in the way. You just see stars, 360 degrees, wall to wall stars. But go into the bush anyway, and you'll still see most of the Milky Way and the night sky. So I want to thank Steve and Deborah for bringing this to our attention. Please try and make a plan of getting it out to more people. I know it's a huge ask for you, but this country appreciates your contribution and what you're doing to advertise this very, very neglected heritage of Botswana. And I wish you all a good evening on the 17th of July. End of story.
Well, thank you, Harold. That was very inspiring, actually, and I absolutely endorse what you said.
Yeah, just 2 seconds. Don't worry. Our call will resume.
And yeah, I think Botswana does have a fantastic opportunity to exploit its night skies in terms of boosting tourism through astrotourism and so on. And I love the Capricorn country quotes that you see on US license plates. Is it Idaho that says famous potatoes or something? Anyway, that was superb. Thanks for that, and we look forward to next month's talk as well. And thanks to Steve and Deborah as well for leading what was obviously a fantastic trip. So without further ado, thanks again, Harold. I'd like to introduce our guest speaker tonight, who is Lucio Piccirillo from University of Manchester. Lucio graduated from the University of Rome, and his thesis was on the cosmic microwave background. He worked for the Italian Air Force and the telecoms ministry, I think, in Italy, and then became a postdoc at the European Space Agency. He then moved across the Atlantic to the University of Delaware and was a visiting professor at University of Wisconsin in the US. He came back to Europe, but this time to the UK, to the sunny climes of Cardiff, which is known to at least one of the people I can see on the screen here as attending very well. And he was senior lecturer and then reader at Cardiff. And then he took up a chair, became professor of radio astronomy technology at the University of Manchester, which is where he's speaking to us from tonight. Among other things, I know he helped to, I think, develop an observatory and planetarium in Vietnam. So he's not just working on the frontiers of astronomical research and technology, but also furthering the development of astronomy and its popularity among the general population of countries, not just in Europe, but outside as well. And I know that we'd love him to come and visit Botswana, and I know he's quite keen to do that in the not too distant future. Anyhow, if Lucio, if you'd like to share your screen.
Yes, thank you very much. Yeah, out of curiosity, where did you get the story of my life?
Well, you know, I couldn't find your phone number or email on the University of Manchester's website, but I could find out everything else about you.
Okay. Well, first of all, hello, everybody. Let's see if I can actually have these things starting. And thank you very much, Michael, to invite me to give this presentation. I'm very happy to give presentations, especially when the audience is diverse, because it's a big challenge. Because I'm pretty sure that we have experts on this in this audience, but I've been told that there are students. Now, the thing is that when there are students, I always go for the students. So, so the experts, yeah, they have to bear with me because I'll be probably too simple for you guys. But well, let's see how it goes. So I thought long and hard about this presentation. And this actually adapted from a presentation that I gave to a high school in the UK, and they went pretty well. So let's hope that it's good this time as well. So I'm going to talk about the origin of the universe, and I need. I didn't get that. So I'm going to talk about the origin of the universe, which is what I have been studying for since I was a PhD student, and I am on the side of the experimentalists. I build the instrumentation, the instruments that provide the data that then the theorists in the comfort of their offices analyze and make beautiful theories about it. Why in the comfort of why I said the comfort of the office? Because usually, in order to have good data, especially in the radio and millimeter wavelength where I work, we need to go in the most absurd places. Most of my measurements come from the South Pole, from Antarctica, and but also on high mountains. And now we are engaged in building a big experiment that will go in the Atacama Desert, which is about 5,000 meter altitude in Chile. Anyway, so let's start. So the first thing that I want to oh gosh, it didn't work. Usually it keeps waving. Anyway, this is a monkey waving, and we start our journey by asking ourselves what is it that triggers the motion, the movement of your hand when you wave your hand, or when you do any action. So, and I'm not a biologist or a physiologist, but I guess I'm not wrong if I say that something in your brain started the action, and this action is mediated by an electrical pulse that goes down from the brain through the nerves to your muscle, and so that pulse, the electric pulse, triggered the motion of your arm and hand. Okay. But then, if you want to keep playing the game, why, then you should ask, what is that made the muscle move? And the answer is there must be some sort of energy that is stored in your muscles. Now, this is something that I the very few, probably the only thing that I understand a little bit is how energy is stored into living organisms. There is a sort of battery, a little battery that is called ATP, adenosine triphosphate, which is this molecule. Actually, I learned how to get a pointer. So I hope you can see the pointer. So this is the adenosine triphosphate. So it's essentially a complex molecule that has a lot of stuff here, but on one edge there are 3 phosphate groups. Okay, and when and this is a little bit of a battery that discharge immediately. So you can make an elementary action by breaking the molecules here, and will generate some energy. And so when this is exhausted, then you have to recharge. And so the energy from the food essentially are taking the solitary phosphate and attach it to the molecule that is missing one. So from 3 groups here, we go to 2 groups here. That's why this is called adenosine triphosphate, as adenosine diphosphate. So essentially, just to say that this process here makes energy available for cellular work, like moving your hand, But where is the energy needed to attach this group to the molecule? And we know that it's coming from food. And now the question is, well, where is the energy in your food coming from? And we know that we get our energy by eating. And so we are animals and we eat. And we eat either other animals or plants. So since animals eat animals and plants, the ultimate source of energy is in the plants. So plants are the primary source of food. And now the question is, but where do plants get the energy? Here we go. So the energy, the ultimate source of energy that runs the Earth, all the activities on Earth can be eventually traced back to the sun. Okay, and that's the sun that does a marvelous thing with plants. So the sunlight, or if you want photons, high energy photons, when they strike a plant, there is a very special molecule in a plant. It's called chlorophyll, and this molecule does wonder because it uses water and carbon dioxide from the atmosphere and generate oxygen, which really we like, and glucose, which is the part of the food that is mostly used in the ATP to ADP conversion. So water and carbon dioxide are taken from the environment, and the glucose and oxygen is released. So plants are really, really important. Now, we've seen so that the source of energy, so we wave our hands because the sun somehow has given us the energy. Obviously, I'm not going to discuss the sun also because I'm not an expert. But the next question that we should ask is, okay, so where is the energy of the sun coming from? And this is where I go and talk about bombs. So, and I'm going to talk about three types of bombs, although the bomb that the sun uses is the fusion bomb. But just for fun, I want to talk about bombs. So the first is a conventional bomb. What is a bomb? A bomb is a device that where a very violent and fast chemical reaction produces an enormous pressure inside usually a metal container, and the debris break. Essentially, the bomb breaks, and the debris are projected all over the place, doing the destruction. Okay, and so there are usually three components. There is the filler. Okay. Then there is, there is the body, sorry. Then the filler, which is the chemical substance that will be subject to a violent chemical reaction. And then there is the trigger, if you want, or the fuse, okay? So when you want to detonate the bomb, you just release a safety here, and you activate the fuse, and then the bomb goes off. So this specific explosion is the one that we are familiar with, so that you can always trace back to a center. So you can, by just studying the debris going all over the place, you can actually trace them back and say where, and estimate more or less where the bomb was and even what kind of energy it had. So the next bomb is much more powerful, and is what is called a fission bomb. So in order to understand this, we need to go to the nucleus of uranium, which is so big, there are 235 nucleons. It is so big that it's sort of unstable, and just one single neutron going actually at slow speed, not even high speed, because if it's too high speed, it might actually go through the nucleus and not trigger the separation into two smaller nuclei. But the thermal neutron can trigger the separation, the division of the uranium nucleus into two smaller nuclei, barium and krypton. And this reaction releases much more energy than just the initial energy of the neutron. So somehow there is some energy stored into the nuclei of uranium. And as a result, you had these two nuclei being released, then a lot of photons, high energy photons, but also, that's interesting, two neutrons that can themselves start a reaction. As you see, then the reaction can become faster and faster. And that's why it's called chain reaction. You see that you generate a chain. So this is how obviously in very, very simple terms, but this is how a bomb works. The only thing that I need to say is that if you take a certain quantity of uranium, if it's below a certain mass, this is called subcritical, then you will not have an explosion. Essentially, these neutrons get absorbed differently before triggering another, the chain reaction. But there is a critical mass above which, if you put together two pieces of uranium, then you are above the so-called critical mass and you can have an explosion. So building a bomb of this type is conceptually quite easy. You have two pieces of uranium that are so critical, and then you detonate a little explosive here, and then you launch this uranium into the other uranium. And so when they are together, they detonate. But in the sun, we have a different kind of explosion. In the sun, we have a fusion bomb. Now, while before energy is released when you divide the nucleus, for very light nuclei, if you put together two nuclei, you actually have a release of energy. Okay, and so this is how an H bomb is done. Think about this: an H bomb uses a fission bomb as a trigger, essentially. So I don't want to go into the details. I'll leave here a little bit of details for those who they have the time and the will to read it later. But the idea essentially is that you start with protons, essentially, and you can actually have a chain of reactions. You can see here actually the speed of this reaction. They are not very fast. In order to have this reaction, you have to wait essentially 10 to the 9 years. So you need a lot of protons to have effectively some of them reacting. But then there is a fast reaction between this nucleus and the helium-3 nucleus. Okay, so deuterium to helium-3, so 2 protons and 1 neutron. And then in order to fuse these into the standard helium, again, you have to wait 10 to the 6 years, a million years. So 1 billion here, a million here. So you say, but why, how is it possible then that the sun is shining with this very slow reaction? It's because you have an enormous amount of reactions there. And so that at a certain point, there is a condition of pressure and temperature that will make this reaction effective. So what we know is the hydrogen, it's here. In this slide, I'm putting 4 mysteries, essentially. So with our journey of trying to understand why, where is the energy when we wave our hand or we do any work, it's essentially due to the fact that that there is hydrogen in the sun. Okay, so that the hydrogen, when under gravity, the hydrogen is condensed into a special condition of temperature and pressure, then it ignites a fusion reaction that self-sustain and give us this energy. So to understand why we're waving our hand and blah, 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 is to understand where is the hydrogen coming from? Why we have hydrogen in the universe? And actually there are other related questions, and each one of these questions is probably a book or more than a book. So I obviously don't have time here to discuss these 4 things. You just have to accept what I'm telling. So the 4 things that are connected to understand essentially the origin of everything are this one. So there is an observation which is the following: why the sky is dark at night. So if we have an infinite, if the universe is infinite and we have an infinite number of stars, then any direction we look, we should see a star. And so the sky should be as bright as the sun, completely brilliant. And instead it's dark. And then there is this issue of where is the hydrogen coming from? And now there are two things that we believe are true. First, based on data on experiment, we see that the universe is expanding. Okay, and this is more or less a calculation that is showing that if we really put together all the energy of the matter and we plug in the gravity, which is actually negative, you discover that the total, you essentially go back to zero. So the total energy of the universe is absolutely zero. So having the universe or not having the universe is essentially the same. Or in other words, you can create a universe having the proper conditions. Okay, and so we believe that the universe actually started because the total energy can start because the total energy of the universe is zero. So the sky is dark at night because the universe is expanding, which is an experimental thing, and because since it's expanding means that there was a time in the past when all the matter was in a condition of very high density. So we are tracing back to the Big Bang. So we are saying that there was a Big Bang, and so that means that the stars haven't been shining forever, but they started shining at some time in the past. Okay, and so that's why they're not filling, if you want, the sky. So that's why the sky is dark and night. So a very simple observation about the dark sky requires quite a complex and beautiful explanation, like the universe is expanding and started with a bang. Now, let me summarize the thing here. So gravity, I don't have the time to go into the details, but gravity allows the creation of matter for free, because at the end, if you put together the numbers, you see that it's zero. You have E equal mc squared, which is a positive energy, as you know, from Einstein, but there is this energy which is coming from if you want the Newtonian, or if you want gravitational theory. And so these two can be made equal, okay, and for our universe, apparently is so. But in order to be so, we need to require that the universe is at least 13 billion years old, okay? And actually, the universe, as we know now, is 13.7 billion years old. So there is sort of some consistency in this model. So that means that matter and energy are created from nothing about 13.7 billion years ago. So you can trace the energy that is moving the arm of the little monkey at the beginning of the talk to the Big Bang. So the Big Bang made the hydrogen that generated the stars, that illuminated the Earth, that generated the glucose into the plants, that was eaten by an animal, that was eaten by another animal, and then it was eaten by the little monkey or the human that was waving the hand. And the hydrogen was generated around 100,000 years after the Big Bang, so quite early on. So this is more or less the end of the talk. The only thing, if you want me to speak a little bit more, I don't know if I have time. I'm sure that I might have another 10 minutes, Mike.
Yeah, no, that's fine.
Okay,
Absolutely.
so I just want to show what we know from data. So what is it that the current model of the universe? Obviously, we don't know in 100 years from now how this probably will be completely changed. But as of today, this is the most coherent model of the universe that we have. So there was a Big Bang, and then there was a time of incredible acceleration of the space-time. There was no matter at that time. Just the space-time was accelerating and inflating, was created and then subject to an incredible acceleration. And then at a certain point, there was the creation, the nucleosynthesis, and then the hydrogen formed. And this is the thing that we observe today. This is the so-called last scattering surface, the time at which hydrogen atoms started forming. And so we are somewhere here, okay? And we're looking with our telescope, we're looking back, and we actually can map this surface, the sky, essentially, how it was 13.7 billion years ago. So there are a lot of things that we don't know. For example, we don't know exactly what happened here between the last scattering surface and when the first stars started to ignite. There is so-called dark ages, and there are an interesting experiment now starting to probe this period. And then the other interesting thing is that the expansion is actually not constant. You know, apparently, and you can see here, it seems that the expansion of the universe is actually accelerating, so it's not constant, and this is due to some unknown cause that we gave an interesting name like dark energy. So whatever we don't understand has to be dark. So there is dark matter, dark ages, you know, and dark energy. This picture will change, I'm pretty sure. Probably my daughters will have a much better figure of what happened in. I'm pretty sure in 10 or 20 years, all of this might change. But there are things that are quite solid. I think the Big Bang is probably quite solid, will stay. But the dark energy, dark matter, and dark ages, some light might be coming on these questions. Now, this is what I wanted to do. So go on a trip from. I mean, this is a random city in the United States, and I'm going to show figures that have a typical scale. So I will show essentially squares, as you can see, where the side of the square is a certain distance. In this case, is 10 kilometers. Okay, and then every picture that I'll show, this is increased by a factor 10. So the next picture would be 100 kilometers. Okay, and so you can see that if you essentially make a square, look at a square that 100 kilometers, you start seeing interesting structures like this is the coast of Massachusetts. Okay, so and then if you zoom again out, and now we are 1,000 kilometers. You now see Long Island and Maine. This is the east coast of the United States. At 10,000 kilometers, now you are like what you would see aboard the spacecraft, and you can see actually the whole of United States and a nice weather system here. But the important thing is you now finally see that the Earth is really spherical. It's not flat. You can testify. You can see immediately that the Earth is spherical. Another jump of a factor 10. And now you can see the planet in its entirety, like you will see the moon from the Earth. So it's like there, it's nice, it's full of colors, very, very interesting place. If you now jump out another factor of 10, you now can see the orbit of the moon around the Earth in just one figure, in one picture. Okay, so you see this is the Earth is in the middle here, and then this is the orbit of the moon. And another factor of 10, and you can see now the orbit, then the Earth and its moon is starting to be small, and the green is showing more or less the path of the Earth orbiting around the sun. So you're starting to have difficulties in observing the orbit of the moon. Another jump of 10, and then now you start seeing the other planets. So you see Venus and you see Mars. Okay, so you start having a feeling of how big the solar system is, and we are at 10 to the 11 meters. So another jump of 10, and now you can see in one picture all the inner planets. Okay, and then there is Jupiter, and I started to see the large, the big orbit of Jupiter. Okay, so these in here, it's more or less where the asteroid belt is. Another jump of 10, and then now you see almost the entirety of the solar system. The one that is outside the orbital plane is Pluto. Poor Pluto, being not being called a planet anymore. Now, another factor of 10, and the solar system start to become small. Okay, we are in what's so-called a Kuiper belt, and we are now starting to be very, very far from the sun. We don't feel the heat of the sun anymore. This is really cold now. Another factor of 10, and we now are not feeling the gravity of the sun anymore. And you can see, you would see if you were there, the Oort cloud. There are a lot of rocks in here, and the sun is just as bright as any other star in your view. Another jump, you actually don't see much difference. Another jump more or less looks like the same. So still the sun is our closest star, but it takes 1 year for the light of the sun to reach us. Now we are 10, now it's better to talk about light years. So we are 10 light years out. So the sun light takes 10 years to arrive to us. And what you see Sirius probably, which is quite bright. And we are going towards Sirius, so it's Sirius the closest star. Now 100 light years from Earth, and we are essentially in interstellar space. We are surrounded by stars, and you will not recognize all the constellation because your parallax is now big. So constellations are gone. You really don't know how to orient yourself in here. Now, another factor of 10, and then you're starting to have a hint that the stars actually are not spread homogeneously, but they are in a structure, which is our galaxy. Okay, and we are 1,000 light years from home. Light now is taking 1,000 years to reach us. And now, 10 to 20 meters, now we are starting to see the Milky Way. Obviously, nobody has ever gone so far and sent a picture to us. It would be impossible. So these are obviously simulations, not real pictures. And here we go. This is what it will look like if we were another factor of 10. We would be just about leaving our galaxy. So we are at the edge of our galaxy, would be just leaving. Another factor of 10, and we have a beautiful view of our galaxy just as a whole. Okay, so now we are in intergalactic space. Another factor of 10, and we now see what we see are not stars, with all galaxies, and we recognize that our galaxy is part of a so-called local group of galaxy, or a local galactic cluster. Another factor of 10, we are in intergalactic space. More intergalactic space. Space is really big. And this is it. This is pretty much as far as we can imagine to go. Okay. In order to see further than this, we need to use different technique like sub-millimeter and sub-millimeter. So our 100 billion light years, we are past the point of the Hubble volume. So essentially, we cannot be in this place. There is no, the general theory of relativity tells us that you are bound in what is called the Hubble volume. So it is impossible to see further than this. However, in the radio, we see, as I said, the beginning. And this is a picture of the universe if you were to look at a few millimeter wavelength. Okay. And so these very interesting and complicated structures can be predicted quite accurately by theory. This is one of the most remarkable things. I couldn't believe my eyes when the experimentalists gave these maps to the theorists, and the theorists came up with a model that was explaining beautifully statistically all these maps. It was a fantastic time for me. I'm really happy that I had to live in a time in which I have seen an explanation for this map. So now we go the other way around. And there is a reason why we go now into this mode, because at the end, the two will touch. And that's how we'll end my talk. Okay. So now we go, we zoom in. So 10 to the 3 meter, 10 to the 2 meters. So at this level, we see buildings. Then 10 meters, at this level, we'll see plants, animals, human beings. Now we are at 10 centimeters, 10 to the 0 is 1 meter. So we see flowers or whatever. Then we zoom in and we see a fly. Zooming into the fly, we are now, the square here is 1 centimeter. We zoom in, now the square is 1 millimeter, and this is the eye of the fly, and it's an amazing complex thing. This, I mean, there is marvelous things also when we go small, not only if we go big. Now we are at 0.1 millimeter, and then you see the complexity of this of the eye of a fly. Zoomed in, zoom in. I mean, there are more and more detailed structures, and now we start seeing other interesting things. Now we see the DNA. This is an actual DNA strand, showing how beautiful is the micro world as well. If we zoom in, we start seeing molecules, and actually this is an image of a real image of a molecule. Okay. And I'm afraid that beyond these we cannot have images anymore. So you see, now we do diagrams. Actually, this is a diagram of an atom, which is completely wrong. I mean, this is not what we believe an atom is. An atom is not a nucleus with electrons orbiting like a planet. I mean, there is quantum mechanics governing this world, and is extremely interesting theory. Is worth a series of courses at the university to learn quantum mechanics. But we are here at 10 to the minus 10 meters, so the dimension, more or less the dimension of an atom. Okay, so let's zoom in, and now if we zoom, we start seeing that there is a nucleus down there. We need to zoom again. We're starting to see the nucleus a little bit bigger. And 10 to the minus 13, we start seeing the nucleus of the atom, where the neutrons and protons are sort of confined. We zoom in again and we see the nucleus. Actually, we don't see, we imagine the nucleus. We can imagine that there are protons and neutrons tightly bound by the strong nuclear force. But if we zoom into one nucleon, like a proton or a neutron, we see that actually they are not elementary, but they are made up of 3 quarks. Okay, and we believe that these are point-like entities, so there is no structure in these things. Perhaps, or not. Well, now it's getting really speculative. Some theorists believe that all the particles are actually vibration modes of a entity called a string. Okay, so and the way in which the way in which the string vibrates determine what kind of particle and what kind of mass and what kind of interaction the particle is. So it's a very interesting theory. It's been around for many decades. Unfortunately, we cannot test experimentally this kind of theory. The energies involved will be stupendously high. Perhaps in the beginning of the universe and cosmology, we can probe this thing. Okay? And some of the experiments that we are planning now might actually go and try to get into the realm of taking numbers that might be verified by string theory, but it's quite difficult. So, and if we keep zooming in, you know, we see these things closer and closer, but we actually don't know what's going on there. We don't know because the energy are above everything that we can possibly even imagine building in any future, in the near future. Someday, perhaps somebody will propose the string that the string are made of something. So instead of just being the elementary constituents, perhaps strings might be made up of something. And so we continue this thing that it reminds us of the Russian doll. It is possible to simulate the quantum mechanical effect that we see, that we think are there. We don't see, we think are there. The only thing that we can see is that there are evidence that reality as such, well, evidence, theoretical evidence, obviously, that reality as such, very small scale, is actually made up of information. There are numbers, essentially each point of space-time, if you want, actually, of the reality that is at the basis of space-time might be related to information. So there is a connection between the super tiny and the huge. Yes, and the connection is here at the Big Bang, because here at the Big Bang, the entire universe, the entire cosmology is as small as this thing. And so when we don't have a theory, but we know that we might be able to one day to get a theory that will tell us how to connect well the small and the huge by studying the Big Bang. And that's why a lot of people are really happy to study the Big Bang like I'm doing as part of my job. And this is the end. Thank you very much for your attention. I hope it wasn't too boring.
Well, thank you, Lucio. That was a fantastic journey through time and space, from the monkey's arm to the depths of the universe. And I just love the paths you've taken us on this journey. I think it's superb. So thank you very much for that. So yeah, I'm sure there will be questions from people. We do have a little bit of time. Somebody who wants to either raise their hand or just speak up.
Wave your hand.
Hi, Lucio.
Hi, Lucio.
Hello.
It's Stephen. No, thank you so much. It's fascinating. Really appreciate it. And I was wondering, but the recent results with the Webb telescope finding galaxies, you know, as far as they could detect, and seeing that they were actually in formation, it seemed like it tossed everything upside down. To see galaxies so far away yet complete. Do you have any insight into that?
Well, the thing is that you know, the farther you look, the earlier in time it is, and so you cannot look infinitely in the past, because the past at a certain point starts at time zero, at the Big Bang. Okay, and so at a certain point, the more distant objects that you see, you don't see formed objects. You see a time in which objects start forming, because you are so in the past that you know, that essentially stars didn't have the time to form and then group into galaxies. Although the James Webb Telescope is producing interesting data, but I'm not an expert, so I'm pretty sure that I don't know if Mike can comment on the latest findings of the James Webb Telescope, that they are seeing objects much farther than previously thought. But in any event, there is a limit of how far away we can see objects, because the farthest away, the more distant in time.
Yes, excellent point.
The dark period after the so-called first explosion, was that not caused, or could that not have been caused by light being blown away completely?
So no, let's see if I can go back to that specific. Bear with me a second. I'll show you a lot of slides. Sorry. I'll go back to the slide where there is a dark age, right?
Mhm.
It's a dark age because we don't see anything there. That's the thing. So we don't know what's going on. I mean, there wasn't time for the stars to, yeah, here. So there is a time we can see very well here the cosmic microwave background, and we know that there is nothing. Sorry. So we see very well this surface, okay, which is the thing that we know that there cannot be other stuff behind, because the radiation emitted by this at this time is black body radiation, and so by definition the black body is not transparent. So even if there are stuff behind, we can't see it. So by definition of black body, it's the perfect black body. That's another thing. You know, there is so much to say about this. I obviously don't have time, but the radiation emitted by the primordial universe is incredibly predicted by quantum mechanics. So it's a black body radiation, and it's the radiation emitted by a body that is perfectly absorbing. So if there are things behind, they're essentially absorbed. What we are now working is an experiment that, instead of looking at the photons the way we're looking now, we want to look at photons in a different way. And so we might be studying stuff behind the so-called last scattering surface. What I can tell you, I'm not a theorist. Okay, so I rely on what the theorists tell me, is that from this time to when the first stars start to ignite, we don't have observation. We don't know exactly what happened here. Okay, so and also the universe was expanding, but was not expanding with the accelerated rate that we have today. The incredible acceleration is the inflation here, but remember, there is no matter here. It's just the space-time that is inflating enormously, and then at a certain point there is the creation and the nucleosynthesis. Okay, so we have hydrogen formed here, and now this hydrogen slowly has to collapse and start forming the first structures like stars, galaxies, cluster of galaxies. But we don't know the details of what happened here. So
is it physically conceivable, you know, as much as light can disappear in a black hole, is it possibly conceivable that intensity could have driven light out, so that the dark ages, you know, could have filled that space?
So one thing that I know is that black holes cannot be very common because of the mathematics. So if you do the maths, you'll see that you cannot have a lot of black holes here. Also because we know that in order to have a black hole, you have to have a star that will be then collapse into a black hole. So there might be some primordial black holes, perhaps, but the theory says, in order to be consistent with other observation, we cannot have too many black holes. So we really don't know what happened here. I appreciate your trying to get an explanation. That would be, if you come up with one, it would be very good. We don't know what happened here, which is actually nice. It's nice to have stuff that we don't understand, isn't it?
Very nice.
Okay, Mapolosi's had their hand up for a while, so do you want to ask your question? Mapolosi? If not,
whom are you addressing?
And Sai is asking, is there any sign of life in other galaxies?
Oh, I don't. It's let's see. The only sign of life in what sense? I mean, we don't have the resolution to see exoplanet in our galaxy. I mean, we are starting to see exoplanets here in our galaxy. Signs of life. It's a very. I'm not an expert. It's a very difficult thing. There are a lot of groups now starting to do study, on exoplanet. And the thing is that we know that life can develop because we are there. So we happened, okay? But we don't know how unique we are. And so it might be that there is other life, but then perhaps it's based on different chemistry, okay? So at the moment, we're doing what best we can do, which is assume that the only life that can form is similar to us. And then we're going to look at the atmosphere. We're going to look at the certain molecules that are organic, and that's the only thing that we can do. But it's really, I mean, the possibilities of life being different from what we think are endless. But as far as I know, there are no signs of extra life beside the Earth, unfortunately. That would be a fantastic discovery the day that we see signs of life on another planet.
Has the James Webb Telescope changed any of these observations, theories?
Sorry, say it again.
Has the James Webb Telescope, yes, changed anything of these theories?
It started operation relatively recently. I know that they're collecting very good data, and I'm pretty sure that there will be much more data to look at. At the moment, as far as I know, there is no indication, but they're collecting data.
Okay. Perhaps is it Raymond actually that you with the hand up, or am I getting your name wrong?
Raymond.
Raymond, yeah. Do you want to ask the question? No? No?
I hope that the level of the talk was more or less embracing the majority. I apologize with the experts, okay, that I was too simple, perhaps.
No, it was really good. Really good. We've got two people with their hands. Ronnie, do you want to ask your question?
Please, we've been looking back. Could you now give us the prognosis looking forward, please?
Oh, looking forward. The expansion will continue, and at certain points, everything will turn off, and the universe will be empty and cold. Is that good enough, or you want more details?
Yes, please. Time frames. Will I be around?
No, we certainly know you. No, we certainly won't be around. Oh well, you never know. At a certain point, biology might be so good that will make people not die anymore. So the expansion is accelerating, and so cluster of galaxies are getting apart. Some galaxies are, but some clusters are gravitationally bound, and they will continue to orbit. The problem is that stars won't shine forever. So slowly they will turn off, and so we'll have a universe made out of cold little pieces of matter. Now there is an issue of stability of matter that is still a question. Okay, so how stable is matter? Will it last forever or not? This is in the unknown. But certainly stars will go off. So there won't be light in the universe at a certain point, and everything will be distant and cold. It's really sad. Yeah.
Okay. And Sai has asked, besides the use of telescopes, have there actually been attempts to visit one of the exoplanets?
No, the only planet we've been is the Moon. They are planning to go to Mars, I guess. To go to another star, they're very distant, So it's a no return. I don't think we can, at least with the present technology, you know, whoever wants to go to another star system, you know, probably it's a one-way ticket. So the thing is that you cannot bring enough resources to leave, you know, or generate a new life unless you go on a planet that is habitable. But at the moment we cannot. With the current technology, I don't think we can send somebody somewhere, you know, like this. There might be some crazy people that be willing to go anyway, but it's a very expensive thing, you know. It's very expensive.
Yeah, the comment here is one-way ticket as well.
Yeah, it's a one-way ticket. Yeah,
Yeah.
As of today with the current technology.
Yeah. So Raymond, Moplosi Raymond has put his question on the chat, and his audio has a problem. And he wants to ask, Roger Penrose viewed the Big Bang as the destruction of the universe before us, not the beginning of the universe. So I'll be glad to hear the comments about this. Also, I want to ask about nothing. What is nothing? So these are fairly deep questions, I think.
All right. I certainly don't argue with Roger Penrose. He's a genius. I really like his work, especially the foundation. I just finished writing a book on quantum mechanics and introductory level quantum mechanics, and I use a lot of style and ideas from Roger Penrose. But he's certainly, I mean, is the thing of theorist. Okay, so I am an experimentalist. I generate data for the theorists to analyze. Okay, and so a theory is something that gives a framework, a model to explain the data. A good theory explains all the data that we know and predicts new data. Okay, now these kind of theories, Roger Penrose is one of these, are very difficult to test experimentally. I think he has suggested some tests, and some of his ideas have been tested and resulted not you know, not verified by data. But you know, keep doing. I mean, that's the great thing to do. Produce theory. We build experiment to verify. If the thing is that we can never prove a theory right. We can only prove theories wrong. I really invite everybody to think about this. We cannot prove that the theory is right. We experimentalists are hated by the theorists because our work usually generates data that destroys some theory. Okay. So the other question was, one, it was Roger Penrose. What was the other? Oh, nothingness. What is nothingness? It's what is before the Big Bang. And there is St. Augustine, you know, there was once was asked, what was God doing before he created the universe? And St. Augustine said he was building the hell for whoever was asking that question.
Oh, dear, very good. So Matthew's got a question here. So I think we've got time for just a couple more questions, but Matthew?
Hi, can you hear me?
Yep.
Okay, I wanted to ask a question more pertaining to his research about telescope design, if that's okay.
Yeah, sure. Well,
I want to...
Lucio, you answer the question.
What's the question, sorry?
I wanted to know how are you thinking about designing telescopes going forward? Because I'm a mechanical engineer, so I was curious about your perspective on this as a physicist.
All right. Okay. This is a quite. I mean, it's a question that that can be answered on many levels. Okay. So I'll keep it, you know, intermediate. Okay. So when we design a telescope is usually to answer a theoretical question. So usually it goes like this: somebody does a simple observation that is generating data that are not part of a current theory, and so everybody gets excited Okay, and the theorists said, oh yeah, we need to refine our theories, and so they make another theory that which predict new data. And so all the experimentalists also get excited, and we design new experiments to look at that specific question. And the thing is that we need technology. So at the moment we are more or less at the edge of technology in terms of the sensitivity of our instrumentation. So what I mean is that you know, when you make a measurement, you're an engineer, you said, right? So you know that if you measure something, you have to deal with noise, okay? And so the lower the noise, the better your measurement is. So our fight is the fight that the experimentalists usually conduct is against noise. And so we are designing better and better experiments with lower and lower noise. Now, we reached the point that in radio astronomy from the telescope that is just one receiver. So you just have, imagine that you have your CCD with just one pixel. That is what a radio telescope has been until 30 years ago, okay? Now we are starting to make kilopixel cameras in the millimeter and some millimeter, where this cosmology stuff is. Compared to megapixel camera, you see there is quite a lot to go on. The thing is that when you make a camera in the optical, you can make a megapixel camera because the wavelength of light is so small that it's less than a micron. So you can make many pixels close packed together, and so you can have a megapixel camera. But when the light that you're looking at is of the order of a millimeter, a megapixel camera it could be 1 to 10 meter side by side. So you understand it's quite difficult. So what we are doing now, we are making the best of our technology. We're making kilopixel cameras, but it means making very big instruments that are very expensive. And the limit is how much the government gives you in a grant. So that determines, you know, how many photons we can detect. I'm pretty sure that our Mike knows very well, you know, the limitation of the government funding. They are limiting the number of photons that we can collect.
Yeah, absolutely. Yeah. Okay. I think we're nearing the end of the time. So I'd like to thank our speaker again, Lucio, for a fantastic talk, incredibly thought-provoking, covered such an enormous amount of ground so well. And our next talk will be on the 27th of July. That's the last Thursday in July. Speaker yet to be confirmed, but same time. And it's great to see so many people turning out on the internet tonight for this from Northern and Southern hemispheres. And so thank you all, and thanks particularly to Lucio for his talk.
Oh, thank you very much.
Thank you. Fantastic. Thank you.
Thank you. Thanks, everybody.
Thank you. Bye. I can
Bye.
stop.
Bye-bye.
Bye.
Bye. Thank you.